I mean, they're not identical, but they're a lot the same. Most of them are just changed numbers. Of course, there are some circuits. There's a multi-loop circuit, capacitor circuit. But like, for example, the capacitor circuit isn't as difficult as the capacitor circuit we had on the exam. What's that? 110 points. So it's 150 total.
Right. I was just
yeah. All right. I'll go through each of the exams. There will be some short answers. So like you've had short answer on various things. So there will be some of those.
Should we just save questions for as they come up in the tests?
Yeah. So I'll just sort of open up each of the 4 exams, and then the questions that y'all have, let me know, and we can work through them. There we go.
Why don't you open up the final? And we can just review that.
Okay.
Or what you do is you accidentally put the final on the website.
I had a student once. She was exceptionally honest, and like at the beginning of the semester, I always do exams 1 through 5, and then I just put in the file after I give it. But the link's there; it's just the file's not there. And I did that. It's like, Dr. Young, exam 2 is up on the. I didn't click on it, but it's up there. Okay.
Oh, so the spot was allocated for it on the website, but you hadn't put the file there yet?
Right. The link was there, but it wasn't linked to anything. Right, yeah. Okay, the multiple choice will be very similar to these, but they'll also be a little bit different. All right, so like let me give you some examples. Like this number 4, where I have the charges, it would be something basically the same except with different charges. So you have to go through the same procedure except, with different charges. You follow me with it? Or maybe one like this, where it asks about the total number of electrons, but just with different numbers in it. Or this one, something similar, but say with different responses. So this just testing the general idea that when I have this negatively charged rod and I bring it up next to this neutrally charged wire, what happens is negative charges run from this end of the wire to this end of the wire. Electrons are what move around, not protons. All right. So as you go through the old test, just look at the questions and think about sort of what is the basic idea behind this, and how could I change that up? Because they will all be changed a little bit. Sorry, computer slow as me today. Okay. Anything in particular in this exam? Probably have some E-fields, these type questions where you change one variable and ask what happens to the other variables. Some types like this where you have positive or negative charges and determining what the signs of those are. Number 19.
Yes. I don't know if you got that yet. Wait. Yeah, that's you.
This one?
Just this one.
This test 1. This one right here?
That's exam 1.
He wants this one, 18. So it's 18.
Okay, the magnitude and the direction of the electric field. Okay, well on these, you first just want to draw your vectors, and this is just a vector problem. Now, we had different vector problems come up, and you will have to deal with some vectors. So just be aware of that. Now, here you want to draw your vectors first. So for example, due to this charge, my vector is in this direction. Right? It's the direction that if I were to have a positive particle there, what direction would the force be? And
assuming that A is positive.
A isn't positive. There's no charge at part A, at point A. It's just a point in space. But you have this imaginary positive test charge, and you imagine that you put it at point A. Remember the test charge? You put it at point A, and then you ask yourself, what is the direction of the force that this positive test charge would feel? Now, charge B, or this negative 6 nanocoulomb, would feel a force in this direction. All right, so then you want to find the magnitudes of those charges. Hang on. So E1, I'm going to call this 1, I'll call this 2. Just find the magnitudes. That's going to be 9 times 10 to the 9th, 16 times 10 to the minus 9, divided by 4 squared. That's KQ over R squared. Look for numbers that cancel out because we'll have a lot of them. And so that's equal to 9 newtons per coulomb. And then for E2, you do a similar thing. It's going to be 9 times 10 to the 9th, 6 times 10 to the minus 9 over 3 squared. That cancels, 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 and cancels, and that leaves 6. And then you want to find the magnitude and direction. So I have a vector of 6 units in this direction. I have a vector of 9 units in this direction, and the net vector is this one. In order to find the magnitude, I do square root of 6 squared plus 9 squared. That is whatever it is, 11. That's right. And then I want to know this angle. 9 over 6, whatever that is. I don't know what it is. 56, okay. Yeah, but it's 56 below the positive x-axis. Are we done vector problems? You'll definitely have a vector problem on the test. Okay. Is that okay?
I'm still writing it.
Oh, okay. All right. But just find the magnitudes of the vectors. With the electric field, you have to ask yourself first, what is the direction of it? Because that doesn't fall out when you do the magnitudes. You use that positive test charge number. So.
You mind reviewing just the concept of problem number 4?
Sure. Can I take this away? Or? Yep. 4. Oh yeah, so here, what are we looking for? The force vectors. So I have 4 different charges. The force on this charge due to this charge is attractive. Oh, okay. Yeah, and
It ends up going into quadrant 2.
yeah, quadrant 2. Because these two are equal and opposite, so they cancel out. This one is that direction, and this one is that direction, yeah. All right.
It's a positive test charge.
Right, but it's a negative charge right there. Okay, exactly. Yeah, be careful on those multiple choice, okay? I think that you could do a lot better, but sometimes you'll miss a lot of points on those. Just read them carefully. Should have plenty of time. Even though it's 8 free response, they're all pretty straightforward. Some of them you're going to be really, really quickly. Okay? Most of the points are still in the free response, but what else on this test? Anything in particular here, Yo? You'll have the same equation sheet that we've been having. All right. Now I go to the next test then. Test 2. All right. Let's see. Looks like this was potential and capacitors, I think we had on this. You will have a capacitor circuit. You have to deal with capacitors. You have several multiple choice questions about capacitance. Pretty sure you had to find the potential of a collection of charges. Don't remember if I had a potential energy or not. circuits. There are no simple circuits like this, but you will see circuits, some resistor circuits.
That would be like the ones from test 2.
Right, more like test 3, more complicated. But not as complicated as test 3. Although you do have a multi-loop circuit, so make sure you're able to solve those. Alright.
Test 3 was the multi-loops and RC circuits.
That's right, multi-loop RC circuits, and it also, I think, again, in magnetic fields in test 3. There are no multiple choice from our last test, because we know you multiple choice on it. It's all free response, but you will see a couple questions, I think, from that test that are similar to the questions on that test. So make sure you know how to apply those equations to Lrc circuits, forced. Did we have forced? Yeah, forced passive circuit. All right. How about on this test? This 19?
Yeah.
And again, yours won't be quite as complex as this, but as you know, the hard part on these is really just redrawing the circuit, and then things sort of start to fall out. So if I redraw this, I get a 12 volt, a 6 microfarad, and then it breaks into a parallel branch. This is right here, breaks into 2 parts. In the upper part, I have a 4. The lower part, I have a 1. And then I have a 2 and a 2 in parallel. And then that all comes back like this.
Pretty much wherever it breaks off, you're going to have a parallel circuit.
That's right. Yeah, so whenever you come to a junction, like here, is here, here, is here, and then it all comes back together right here. So like I could take all of this and just collapse it down to a single point, which is what I did right here. It all became a point, because there's no devices between those various junctions. All right, and then from that, you want to find the equivalent. Don't forget your rules. This is 4, and then 4 and 4 becomes 2. Don't forget those really simple. Well, these are on the equation sheet?
Give the one for resistance.
Oh yeah, the rules for, right, the equations for determining the equivalent. Yeah.
But not like if they have the same voltage.
Right, no. Alright, so I have these two, this 4 and this 4 combined to give me a 2 microfarad. So I have a 6, a 2, a 1, 6, 2, 1 microfarad. The 2 and the 1 combine to give me a 3, and then I'm left with a 6 and a 3 in series. Across a 12 volt, and then the equivalent of that is 1 over 6 plus 1 over 3, the inverse of that. So my equivalent is 2 microfarads. It'll help you to sort of have those numbers on the tip of your tongue. What is a 4 and a 4 in series? What is a 3 and a 6 in series? Because those are just common numbers, and you'll see some on the test tomorrow. It'll be very, very similar, number-wise. I mean, the circuit is all different, but just the way the numbers are paired up is similar, because it makes it easier to work out. Okay, and then it'll also help you to be able to look at something like this, say this 6 and this 3 microfarad in series, and realize that because this is a big capacitor, Q equals CV, if C is big, that means V has to be small, and it has to be smaller by a factor of 2. So that gives me what voltage across the 6? Not 8, it's the small one. 4. I get 4 volts here and 8 volts here. Alright, I get the smaller by a factor of 2 on the bigger capacitor. So if I get 4 and 8 volts, that means I also have 8 volts here, and 4 volts here. Was this a 4? Yeah. So I have 8 volts across this 2 ohm resistor. That means I have 8 volts across both of these, which means that I have 4 volts across this 4 microfarad capacitor, and across these two microfarad capacitors, what do I have? they're in parallel, so they have the same voltage, so they each have 4 volts and 4 volts. And then I think that's about it. I know that I have 8 volts here across that 1 microfarad capacitor, and I think that's all of them. Then it's really just a matter of pairing them all up. So C3 was the 1 microfarad at 8 volts. C2 was this one, it's 4 volts. C1 is right here, it's 4 volts. This 2 microfarad was 4 volts. C5 is 4 volts. Does that make a lick of sense? Your circuit will be a little simpler than this. There'll be fewer devices. I think there were just like 4 capacitors in it, which may seem not like that much less, but it makes the circuit a lot easier. Okay? Y'all can do this? Yeah, and then to find Q, you just do Q equals CV. So once you know the voltage of the charge, it's really easy to find the third thing.
What's the E5 again?
E is your energy, and it's just 1/2 CV squared. That's on your equation sheet, but it's just the energy stored. So it would just be 1/2 times C, which was for E5 was 2 microfarads times 4 squared, 16. So 16 microjoules. Who? Yeah, Christian.
I just have trouble breaking it down into the different circuits.
Mm-hmm.
Visualizing which one.
Yeah, that'll be important. It's important for you to know how to do that. Let me step back through this. Yeah. Well, hopefully you never really get to the point where you're dealing with numbers so much, because hopefully you can look at it and just see the relationships and how the voltages are separated across the circuits. But yeah, the hard part is just drawing this circuit so that it looks like something that we've dealt with before. So you want to start on the big side of the battery, the positive side, go through the circuit, and look for these junctions. All right, and whenever you see a junction, it splits into parallel branches. How many splits you have, that's how many branches you have. So we would be looking at, this 12-volt battery, 6 microfarad. We come to a junction, it splits into 2 because I have 2 branches here. Taking the top branch, it goes to that 4 microfarad, and then it comes to another branch. So I have my 4 microfarad, and then another branch right here where I have those 2 capacitors here and here. And then coming on the bottom branch, I just have that 1 microfarad capacitor. This was a 2 and a 2. And then that all comes back together. It's really practice. Like if you need practice on that.
Like, is there any extra problems?
Yeah, every test that we've ever had has one of these problems. And in the homework, and we did a couple problems in the notes too. So yeah, I would look back and see how those are broken down. All right. You definitely see one of these. Make sure you can do them. It'll be not this complicated, but I think you should be able to do this. All right. There are a lot of questions, so I tried to make them a little simpler. All right. What else on this test, Joe? 15. Okay, 2 capacitors, blah, blah, blah. What is the equivalent? Looks like they're in series. The first thing you have to do is to calculate what is the capacitance of each. So capacitance is kappa epsilon naught A over D. That's on your equation sheet. The first one, C1, has a kappa of 1. It doesn't have a dielectric. And if you don't have a dielectric, just you leave that out. Epsilon naught is 8.85 times 10 to the minus, what, 12? That's on your equation sheet. A is given, 0.004. And D was given, 3.54 times 10 to the minus 8. I think that was really even numbers. Anybody know what it is?
1 times 10 to the minus 6 is what I got.
Okay, so 1 microfarad. Is that right? 8? Yeah, that looks about right. Is 1 microfarad? Okay, so that's C1. And then C2 has a dielectric. So C2 is kappa times C1. Because all the dimensions are the same except the dielectric. So this is equal to 2 microfarads here. All right. And then we want to know the equivalent capacitance. So it's going to be 1 over 1 plus 1 over 2. 2 halves plus 1 half is 3 halves, so it's 0.67, or 2/3. Alright, you with me? This goes back to like the circuit we were doing. Like the previous circuit we were doing was a similar thing. Here, if I want to know the charge on each, the charge on each is the same as the charge on the equivalent, because capacitors in series have the same charge. So the equivalent capacitance has a charge equal to C equivalent times V, which is going to be 0.67 times 12. That's 2/3 microfarads times 12 volts, which is 8 microcoulombs. But because they're in series, they both have 8 microcoulombs of charge. Right. And then if you move the dielectric, how does the charge increase, decrease, or stay the same? Well, if I remove the dielectric, I have these two capacitors. I have C1 and I have C2. If I remove the dielectric, that means this capacitance goes down. That means that the equivalent capacitance does what? If that capacitance goes down, what happens to the equivalent capacitance? Huh? Right, so that means that the equivalent capacitance increases, which means that the charge on both of them increases. Is that right? Is that the right answer? Yeah. Let me think. So I remove the capacitor. No, the equivalent capacitor decreases. Yeah, the equivalent capacitance decreases here. If this capacitance decreases, this capacitance also decreases. Yeah. So they're both going to decrease. If the equivalent capacitance decreases, they'll both decrease, because my equivalent charge is equal to that equivalent capacitance times V. Alright? Okay on this? Alright. Can I clear this? How are y'all studying? Okay. So did you say you're not studying?
No, I haven't started yet.
Okay. Alright. That's fair. Okay? Can we go to the next one? Are y'all okay with this one?
If you were to just work out the help, that it would end up being 1 over 1 plus 1 is 1/2, right?
Yeah, so if I find my equivalent capacitor, it's just going to be 1 over 1 plus 1 over 1. 1/2, right. Yeah, if you want to plug in the numbers, that's fine. And the equivalent was, what, 2/3, right?
Yes, sir.
Right.
I was just trying to see the math that supports it.
Yeah. Mm-hmm.
Concept.
Okay. Alright. Go to the next exam, Neil? I don't think it's a terribly difficult exam, but you know. I think it's pretty straightforward. Because if you're prepared on all these exams, you'll do well in the finals. Alright? You You will have a multi-loop circuit, but you will not have the opportunity for extra credit. So with the Gaussian business, so if you want to do that, sorry, you can do it on your own at home. I'm sorry, any of the multiple choice stand out to you? You'll have to do the right-hand rule, some, that shouldn't be a surprise to you. Basic stuff about household things, PFCI, circuit breaker, and sort of basics of the household circuit, the grounded outlet. No, you could have a free response. In fact, you had a free response on this exam about it, just to describe one of those things. I don't remember if it's on there or not, but it could very well be. I know I did put a couple sort of short answer type questions. All right. Don't spend too long on those. Just write a couple sentences. That's all I'm looking for. Just make sure you get the main ideas. Well, some people will just write like a whole page, and eventually they'll get to the main ideas, but they could spend a lot less time if they just wrote a couple sentences. All right, you will have a multi-loop. Y'all are okay on this? Find the magnitude and the direction. Yeah, it's good for review. So here, first thing you do is pick directions for the current. Doesn't matter the directions. I'll just pick random directions. Then you write equations. I'm going to start here, going in this direction. That's going to be -2 volts. Coming through here, -2I2 plus 4 -2I1 equals 0. Coming along through here. Go back and review those rules if you're not sure how I got those signs. I'm going to go on. If you have a question about it, I can come back to it. We'll take, say, here, go in this direction. That is going to be +8 -4 plus 2I2 equals 0. And then I can write my third equation. We'll do it from the junction rule. Just pick a junction, doesn't matter where. Incoming currents are I1 and I3. Outgoing is I2. So that's going to be I1 plus I3 equals I2. Yours will be simple in this way. This is a really simple system of equations to solve because one of them only has a single variable, so I can solve this. That's 4 plus 2I2 equals 0, so I2 equals -2 amps. That means that I2 is 2 amps, and it's up. It's negative, so I chose the wrong direction. You with me on this? You can write the equations. You follow what I mean by the signs? I need to review those. All right, let me just review one. So let's go to this one right here. 8. I'm going in this direction. It's 8 because I'm going from the little side to the big side. It's -4 because I'm going from the big side to the little side, from high to low potential. It's plus 2I2 because I'm doing what? Going against the current. And then I come back to the closed loop. On this, we're looking at, this is an application of the loop rule, right? So listen, it's a closed loop. It has to begin and end at the same point. Y'all know that, right? To begin and end at the same point. It's a closed loop. That's what a closed loop is. Okay, so once I know I2, I can find I1. Up here, I just plug in I2. I1 is equal to -2 plus 4 plus 4 divided by 2. That's 3 amps. I think I did that right. I1 then is 3 amps up. It's positive, so it's whatever direction I chose. And then to find I3 is equal to I2 minus I1, which is -5 amps. So this is 5 amps down. All right, you're gonna have to do one very, very similar to that. Just different numbers, different resistors, different layout, but a 2-loop circuit like that. You have to write the equations. You have to solve the equations. There'll be a similar set of equations like this. Okay, go with me on that. You can do it right now and get it perfectly right. I think you probably could, if you didn't have pressure. But tomorrow I'm gonna be yelling at you. I'm gonna be like right up in your face. What are you stupid? You can't do this wrong.
Imagine if you yelling.
Oh yeah, I can yell. Can I clear this? You want to try that tomorrow? See how you do under pressure. So what's that?
So if you're doing that, I'm bringing a box of tissues.
Oh no. Okay. Here's that question about household safety devices. Any of these stand up to y'all? RC circuits. This is really just knowing the equations. They're on the form. This is really just a cross product. I think y'all are pretty good at that now. But if not, let me know. I can work through any of these. This is the cyclotron equation for a mass spectrometer. All right. Any one of these in particular? Which one? Which one? All right, 15 and 17?
Yes.
Okay, I'll do 17 right now. Okay, so we had 3 household devices. We had the third prong, our grounded outlet. I always call it a third prong, but it's a grounded outlet. Couple major ideas.
For some reason your number system off. We want the
Oh,
one above one's on that.
oh, okay. This one? The one after. This one right here?
That's the one that's 17 on our test.
Oh, I'm sorry. I must have, I guess you had one fewer or whatever. I don't know what happened. All right, so when connected, the battery will discharge the capacitor after 10 seconds. First thing you want to do is just ask yourself, what is the time constant? And our time constant is equal to R times C. So R times C, that's 1 times 5, so that's 5 seconds. So for example, if this said 50 seconds, then you would just say it's 0, because after 0 seconds, oh no, this is a charging capacitor, excuse me. It would be whatever the maximum charge is. You also need to know that maximum charge, that's just equal to C times V. Sorry, let me rewind. It would be at the maximum charge because it would be 10 time constants. And after 10 time constants, it's fully charged, or fully discharged. So if this was 50 seconds right here, it would be whatever the maximum charge is. The maximum charge is 5 times 30, 5 microfarads times 30 volts. That's equal to 150 volts. And then you just want to know the charge at 10 seconds. These are on your equation sheet, but your expression looks like this. That's the 1 minus e to the minus t over RC. Right? Remember, this is that function that looks like this. So it's asymptoting up to that maximum charge, and then you just put in the numbers. Sorry, this should not be 150 volts, microcoulombs. 150 microcoulombs, 1 minus e to the minus 10 over 5. I don't know what that number is, but make sure that you can do the exponential for on your calculator. And then how long does it require for the capacitor to become fully charged? Remember, this is 10 tau, so that's equal to 50 seconds. And then sketch a plot. This is our plot Q versus T, where it maxes out at that maximum Q. All right? Mark? Okay with that? Yeah. Yes, you can see one like this. I don't remember if there is one or not, but certainly could. I pulled 2 questions from every test. Changed them up a little bit. All right. And what was the other one? Don't give me the number. Just tell me what it was like.
You want to put the resistors?
Okay. Can I clear this then? So I could change this, for example, and ask for it discharging instead of charging. And then the problem changes a little bit. You get rid of this 1 minus, that's not there. And this, instead of looking like this, it looks like this. For example, I haven't really changed them a whole lot. They're mostly a lot the same as the old test, but that would be, if it had this question, that's probably how I'd change it. All right. Resistors. Yeah. So under the voltage, looking at these really help you to sort of know those easy numbers, have them right on the tip of your tongue so that you know how this all falls out. First of all, I find this 1 plus 2, that's 3 ohms, and then I have a 3, a 6, and a 2 ohm, all in parallel. And 1 over 3 plus 1 over 6 plus 1 over 2. The inverse of that, of course, is 1, right? So I get a simplified circuit, which is just a 2 ohm and a 1 ohm resistor with a 9-volt battery. That means I have a combined resistance of 3 ohms, which tells me that I have 9 volts over 3 ohms amps, which is 3 amps, which tells me I have 6 volts and 3 volts, because 6 volts is 3 times 2, 3 volts is 3 times 1, V equals IR. Alright, so I can go over here and can start filling in some of my values. I didn't ask you for all the voltages, but you can easily fill them in. I have 6 volts here, I have 3 volts here, and 3 volts here, and I have 3 volts shared between these two. I have 3 volts across 3 ohms. What's the current through that middle branch? What is it? No, not 3 amps. Through this branch right here, what's this current? I have 3 volts of potential, 3 ohms of resistance. It's going to be 1 amp. So I have 1 amp of current. That means I have 1 volt and 2 volts here. That's just I times R. 1 times 1 is 1, 1 times 2 is 2. So that's basically, oh, and then the total current is right here, 3 amps. V3 is 1 volt. Let me see what else was asked. These are going to get off one. And then I2 is, what's I2? Up here? Right, I is V over R. That's 3 over 6, which is 0.5 amps or half an amp. Okay. It's a lot like the capacitor circuit, so you just have to think about how things are distributed. But things are distributed differently. You might want to go back and revisit those rules about capacitors in series and parallel and resistors in series and parallel, because they have similar but slightly different rules. Any other ones on this test?
Do you have the screencast videos and all the tests?
Yeah, they're all up on the website. Yeah. Yeah, I'd recommend that. I really recommend that you go and print out the tests and you just work them on your own without any help, and then go back and maybe grade yourself on it and see how you do. I mean, that should take you, well, that could take you up to 4 hours to work through all of them. But, you know, you got 16 hours between now and the test.
Do it 4 times.
Right, so you can do it 4 times. Hey, listen, I made 112% on my final the other day. Man, I was studying up a storm, huh? Well, he had some extra credit problems. I had little flashcards. I had things in my iPod. I listened to everything about 4 hours.
What was the best grade I've heard of ever out loud?
What, 112%?
Best grade I've heard was the last calc test we took. One of my buddies made 106 or something like that.
Oh, yeah.
Cody did.
Well, this is an easy class. This history class. All right, what else on this? Go to the next test, is that okay? All right, this is the one we just took. Oh, partial derivatives? Yeah. They're pretty simple. No, that's not it. Is it? No, that's the cross product. You want to look at the cross product or the partial derivative? Okay. All right, well, here, this one's pretty straightforward. I just wanted to do the cross product, QV cross B. We've seen a lot of cross products, so you can see it tomorrow. Q is -10. Make sure you carry your signs. V is 3J minus 4K. cross B, 1I plus 2J. If you're in Calc 3, none of you are in Calc 3, are you? Well, if you've learned a different way to do cross products, that's fine, but if not, I wouldn't do it now. Alright, you just do FOIL. So I have negative 10 times 3J cross I. That's first. Outer is 6J cross J, but remember J cross J is equal to 0. Inner is minus 4K cross I. And then last is minus 8K cross J. Okay. And then I want to find out what all those are. This is I, J, K. You want to use your right-hand rule to determine what these are. So J cross I, J, I is in that direction, so it's into the page. That's the negative K direction. K cross I is in the positive J direction. And then K cross J is in the negative I direction. So you just want to use your right-hand rule. Fingers in the direction of this one, they fold towards this one, and then your thumb gives the result. So J cross I was what, negative K, is that right? Is that right? And K cross I was positive J. And K cross J was negative I. So that's times, all that times 10. So negative 30K minus 40J plus 80I in newtons.
Would it become negative 10 or no?
Oh yeah, negative 10. I'm sorry. Yes. So 30K, 40J minus 80I. And you want to look at the partial derivative too? Was that this exam or the previous one? I think it was the previous.
If you asked for the magnitude, it would just be the Pythagorean theorem, just square everything.
That's right. Yeah, so vectors in 3D is just the square root of all 3 squared, the sum of those. And I won't ask you the direction. The angles, you have like 3 angles, I guess, to define it. Is it 3 or 2? To define a vector in 3D space. I think it is 3. It's not complicated, it just takes time. Mhm. I gave it to my little girl to doodle on. No, I think I gave it to you. I'm pretty sure I gave it to you.
Wednesday or
Yeah, that was it.
Were you there?
Wednesday.
Okay. Alright, so here, to find the electric field, remember the electric field in the x direction is negative del V del x. Just taking the partial of this function with respect to whatever variable. So to find the x component, I'd say negative the derivative of v with respect to x. I just treat all other variables as a constant. So I have 3y squared x. That's just going to be 3y squared. Minus 2xy minus 2y. And then I plug in my values for x and y, and I get the value I get. Negative 3 minus 2, 1. Alright, let's do one that's, let's do EY. It's just like a derivative, except you're holding the other values constant. That's going to be, what's this one going to be with respect to y?
6yx minus 2x.
That's right, 6yx minus 2x. Alright, with respect to y, then I hold the x variable constant. It just becomes a constant, so it doesn't affect the derivative. You just sort of pull it out. Alright, and that's going to be equal to negative 6 minus 2, or negative 4. Those are the x and y components of the electric field. So this is in the I direction, this is in the j direction. Alright. How about exam 4? Okay. Alright, let's see, we had Faraday's law here. Well, yeah. Oh, it's on my desk. I'll grab it for you. Just come see me afterwards. On this one, a lot of people miss this part D because they didn't, and when you add 5 turns of wire, the induced EMF is increased by a factor of 5, but the resistance is also increased by a factor of 5, and they didn't take that into consideration. I didn't mark that much off, but they didn't consider that. Here's an Lr circuit. A lot of these are really just knowing the equations. You have that equation sheet and knowing how to apply them. They're labeled, so you need to know what the different circuits are called. You might just go back and remember, well, this has a resistor and an inductor. It's an Lr circuit. This one works a lot like the Rc circuit. It follows that exponential. This was an Lc circuit. Remember, this is the one where the energy transfers back and forth. So to find the current, you do like we did with the spring, where you say 1/2 Li squared is equal to 1/2 Cv squared, or Q squared over C. Know how these things work. I could ask you some free response type questions like I did here, and be able to know what the functions all look like. I'll certainly ask you to draw some of those functions. There's an Lrc circuit. Remember, this is the one that starts out with a big charge, and it has both a sine function and an exponential function that causes it to decay. Any of these stand out to you?
Number 7.
Phasers, okay, 7. Transformers. Okay, 7. Let's see. I'm going to pull up the equation. I don't remember all these things either, so let's pull that up. Remember, this was the one where we were dealing with the vectors for the phasers, and when we did the vector math, you get these expressions for z and phi and omega and all that business. So here we wanted to know of this Rlc circuit. Oh, this is not, okay, so this is not a forced oscillator. Oh yeah, it is. Yes, it is. Yeah. When I say forced, it's because it has this this EMF of 12 volts. Whereas the previous one was an Rlc circuit that was just passive. It didn't have a generator, and so it decays over time. But this one continues at the frequency of the EMF source. So a couple of things I want to find. First of all, what is the maximum initial current? So A, that's just going to be I equals to my EMF divided by my impedance, my overall impedance. And my impedance is based on this R squared and XL and XC. So it's really just a matter of getting those values for XL and XC and calculating the overall impedance of the circuit. So XL is omega L here. Okay. So XL equals omega L. XC is 1 over omega C. And then you want to calculate both of those. Now omega is not given. Instead I give you the frequency. But omega is equal to 2 pi times the frequency. That's on your equation sheet. Somewhere here it is right here. Which is equal to 120 pi. Yeah.
That one I think I missed because why wouldn't you use the resonant frequency?
Yeah, I use
That's what I use on the
I
test.
use the 1 over LC.
Oh, because it's not operating at the resonant frequency. Yeah.
I just saw omega and
Oh, okay. I see. You did 1 over LC. Remember on these, when you have a forced oscillator, they always operate at the frequency of the generator. They operate better when they're at the resonant frequency. So you'll get a bigger current at the resonant frequency, which is really that natural frequency for the LC portion of the circuit, because you get this interchange of energy back and forth and back and forth. And if you match that frequency, then you get a better response in the current. But it always matches the frequency of the generator. It doesn't have to be the same as the resonant frequency. Yeah, I think I remember seeing y'all do that. So here XL is omega DL. Yes.
For that portion, you would have to use
Right. That's right. Yes. Yes, you will have to switch, in fact. I don't think I'll try to get it in the copies, but if not, remind me and I'll tell you which ones you need to be in radian mode. But it's only going to be in these. Just make sure you check it before you do that. It makes my life easier. I'm not going to count off much if that's the mistake you make, but it makes my life easier. I'd rather everybody have the right answer, because then it's a lot easier to grade. Okay? Well, I mean, I still look at the work, but, you know, it's a lot easier if it's the right answer. So I'd really appreciate that, to be able to do that. Okay? Get the right answer. Okay. Huh? Oh, yeah.
Yeah, it's not something we have a semester just to get a test back.
Okay.
Yeah.
Anyway, so you find XL and omega and XC. Is it okay if I skip finding these numbers? I don't know what they are right off. But it's just omega L is going to be 120 pi times L, which was 212, so that's 0.212. And then this is 1 over 120 pi C, which was, really? No, 66. Oh, is that the value you mean?
That's the value of amplitude.
Okay, whatever those are. And then you find, once you get that, you find the overall impedance. And then that tells you what your overall current is. 12 volts over whatever Z is, which you get from this Pythagorean theorem. Okay? Is that okay skipping over those numbers? They're on the website too. So, and then if you want to know the phase constant, you just take that XL and XC, those reactances, that's what the XL and XC are, and find the phase angle. And then once you get that, you can write the expression like here. So once you know I max, right here, and once you know phi, which is what you calculated here, and once you know omega d, well, omega d is just the driving frequency, that 120 pi. You can just plug in those values, and it gives you a function. And then if I ask for the current at any particular time, you just plug in that time. And in the radian mode of your calculator, using radian mode, calculate that current.
So like if you ask like in any of the questions where it just says write the expression, you're just looking for like the formula?
Mm-hmm.
You're
Yeah.
not looking for the ex-
No, I'm just asking for you to recognize that this expression defines the current as a function of time, and then you have to find the various things. You have to find the maximum value, and you have to find the phase constant and the angular frequency. It's similar on the others, right? I give you, like, here's the charge for the damped Rl circuit. This is the current for the resistor circuit, though you didn't have one on your test, so you won't see that. All right? Does that answer your question? Is that okay stopping there? This is really just plugging in the number there, 0.1 seconds. And then this is drawing those phasors where we had, this is my VR. I should forget which one lags. VC, oh yeah. And then VL. You could see that phasor problem too, like the one previous to this.
What was the thing that you gave us? It was like Leo the Iceman or something?
Eli the Iceman.
Eli the Iceman? Okay. And that's for the phasors, like you could say that L comes.
Yeah, so yeah, the voltage of the inductor leads, the voltage of the capacitor lags after. All right. Can I clear this, y'all? A lot of this test was just having the right equation. You have the equations, so it was really just sort of plugging in the right things. I'd say it was an easy test, but I think y'all did pretty well on it, if I recall. Right? All right, anything else on this test?
Put 8.
Huh?
Put 8 of 8.
Yeah, that was easy, wasn't it?
Yeah, just put 8 of those.
Okay. All right. Yeah, we had a damped Rl circuit. Rlc circuit, rather. Yeah, this one, number 4, this is a damped Rlc circuit. It doesn't have a battery in it or power supply. It's oscillatory because it has the capacitor and the inductor, and it's damped because it has the resistor. You know what I mean by I say damped, right? Normally, if it didn't have the resistor, the charge would look like that. But because it has the resistor, the charge gets smaller and smaller and smaller. It loses energy to the resistor. The resistor dissipates heat, and it loses energy. All right. I can drop this. Any other questions? I don't think we had any dot products, did we? No? Yeah, because of our magnetic forces. Nope, no dot products. Well, we sort of had it, but it didn't come up on any of the tests. When you're calculating the flux, yeah, that was, but it didn't come up on any of the exams. You won't see it on the thing. All of our flux calculations were very simple because the vector was always perpendicular to the area, and so the dot product was 1. Or excuse me, the vector were parallel to the area. 20 multiple choice. Yes, they're like the test questions. Study the 4 exams that we've taken this semester. They're not identical, but they're very, very similar. All right. Want to see our cat right quick? Y'all care? We got a cat. My son said he was uncertain about getting a cat because he didn't think he was going to like it. He said, "This cat is so cute, I could rip its head off." But he was just sort of, you know.
That's how it works.
Yeah.
It's hiding in the bathroom right now, but it's a cute cat, is it not? Like, I'm not a big cat person, but yeah, it's a little bitty kitten. I don't know. It's my daughter's cat. She's very indecisive.
Yeah.
It's going to be the most spontaneous name. Comes off the top of my head.
Well, we've been through Dude, Levi, Kit Kat, Fozzie. Dude, that's what we always did. When I was a kid, we had country cats. They were all cat or kitty. Yeah.
I was gonna say, if it was a girl, I'll bet money the name becomes Fee.
Becomes what?
Fee.
Fee? Oh yeah. Maybe we could do a Greek letter. I think Almanzo is the most current name. Like from Little House on the Prairie. That was the husband of Laura from Mary, one of them, when they came an adult.